Bismillahirrahmanirrahim. So now we're going to continue our lesson on the wave sections. Okay. So for the wave is defined as motion of disturbance. Okay. So vibration is source of the wave, as we know. But for the wave itself, we can classify wave into two types of wave, mechanical wave and also electromagnetic wave. Okay, for the mechanical wave, we may have, for example, sound wave, seismic wave, ropes and string, and then water wave. For the electromagnetic wave, for example, the lights. Okay, so the sunlight, the ray coming from the sun, okay, or the star, okay, travel through the vacuum to us on the earth. Okay, so what is the difference and what is the similarity between mechanical wave and electromagnetic wave? Okay, the similarity, they transmit energy, okay, but then they do not transmit matter. The medium is not transmitted through both of the wave. Okay, some of the wave may use medium, some of the wave, the other wave, the EM wave, does not need medium. But for mechanical wave, yes, we do need the medium, okay, to transfer, okay, the wave, the energy. So for the EM wave, the characteristic, it can travel through vacuum of empty space. Okay, how they're going to move? They're going to move in terms of transverse wave. Okay, but for mechanical wave, it requires a medium, okay, the matter, to travel. Okay, how they travel, they have few pattern or types of the way they travel or move, whether it's in terms of longitudinal wave, compressional wave, or transverse wave. Alright, so in this syllabus, for your syllabus, your level, we are going to focus on the mechanical wave. We are going to look for electromagnetic wave during physics 2. Alright, so mechanical wave and its properties. Okay, as we know, wave is motion of disturbance. For mechanical wave, it requires source of disturbance, the medium that can be disturbed, then of course some physical connection between the source of disturbance, which is the vibration, and also the medium. If the vibration, the source of disturbance, does not in contact physically with the medium, the energy cannot be transferred. The disturbance cannot be transferred. Okay, all waves carry energy and momentum. So type of wave, we have traveling wave. Later on, we will see standing wave. Okay, so first thing first, let's take a look on the traveling wave. Okay, when we talk about traveling wave, it means that the wave itself going to travel through the medium. For example, okay, we have a stretch string like this. We flip one end of the long rope that is under tension and fix at the other end. The pulse created just now going to travel to the right with definite speed. A disturbance of this type called a traveling wave. Okay, so types of wave depends on the way it travel, right? So for the transverse wave, okay, what does that mean? Okay, for example, we have a springs here fixed at one end, the other end we shake it, okay, we pluck it up and down. So in transverse wave, each element of the medium that is disturbed move in a direction perpendicular to the wave direction. In this situation, what is the wave direction? The pulse is traveled to this direction. Okay, so this is the direction of motion for the wave. Okay, and the medium is shake up and down. Okay, therefore, okay, the medium is shake up and down. Therefore, it's perpendicular. okay, to the wave motion. Okay, so this kind of situation, for this kind of wave, we call it transverse wave. For longitudinal wave, okay, we do the compression and rarefaction to the string here, to the spring here. So the motion of the medium is parallel and anti-parallel to the motion of the wave. So the motion of the wave in this direction, okay, and the vibration of our spring is left-right. So parallel and anti-parallel. This kind of method, we call it as longitudinal wave. Okay, waveform. Okay, a picture of wave that is in motion or traveling wave. Okay, let's say we have brown curve here is a snapshot of the wave at some instant in time. The blue curve is in later time. So after t has passed. So this is at t equivalent to 0. We have the brown curve initially. After some times has elapsed or t become t. Alright, now okay, the wave already in term of blue color here. So means that it's already traveled. How far it has traveled? This is the distance traveled by the wave, which is v times t, the speed of it times with the time taken, because the v is defined as distance traveled over time. So to have how much it's already have traveled, so vt is equivalent to d. Okay, so this is actually what is happening. Okay, the high point known as crest. Okay, the low point known as throw. Okay, hopefully you still remember this. Alright, longitudinal wave represented as a sine curve. Okay, a longitudinal wave can also be represented as a sine curve. Compression correspond to the crest and stretch correspond to the throw, also called density wave or known as pressure wave. So for the rarefaction region here, okay, the one that we have stretch, okay, correspond to the throw. So this is the throw, okay, correspond to this area. All right, and then for the compression region here, correspond to the crest. Okay, so in terms of, right, this is actually stretches happen, and here is the compression. Okay, compression. So hopefully, okay, you may transfer the info when the question asks for comparison. Okay, producing the wave. Okay, so characteristic of the wave, let's say we have a stretch string connected to a vibrator, a blade of vibrator. So this blade, let's say we consider one point, okay, point P here. Okay, of course initially the blade going to move downward. Okay, so consequent of this, the point P going to move downward, right? Okay, so this is at t equivalent to 0. So from the distance from crest to crest or throw to throw is lambda. We call it wavelength. Okay, one wavelength is a distance between successive crest or successive throw. That is 1 lambda. So at t equivalent to 0, the position, the initial position of point P is here. After 1/4 of period has elapsed, okay, so point P now moving down, okay, and then forward more in downward direction, so it reached this position within half of the period. Okay, and now whenever it reach equilibrium position again, it's 3/4 of the period. If we have figure E there, okay, whenever the point P return to its original position, now the period is capital T, 1 complete period. Okay, description of a wave. Okay, a steady stream of pulse on a very long string produces a continuous wave. Okay, because the blade keep on moving, let's say. The blade oscillates in simple harmonic motion. So, vibration of the blade producing a wave. Okay, that is how we know. Okay, it is in simple harmonic motion because it keep on moving up and down towards the equilibrium position. And it's obey Hooke's law. Okay, each small segment of the string, such as point P, oscillate with simple harmonic motion as well. Let's take a look on this graph. If we have Y versus X, so what is this? Before this, we've learned about position or displacement versus time. Now we have, okay, this is also a position or displacement. This is also position or displacement. But then there are different things actually. Here, along Y here, is the displacement or position of your medium. The string, the spring, could be any. The medium, the displacement of the medium. The X here is the displacement of your wave. How much the wave has been traveled. Okay, what is the position of the wave after T has elapsed. Okay, that is the meaning. Then for the Y is the maximum displacement, if we're talking about this point, is maximum displacement of your medium, the string, the spring, depending on which medium you are using or referring to. So, maximum displacement from the equilibrium position is defined as the amplitude. Okay, and the wavelength is defined as the distance between two successive adjacent crest to crest or throw to throw. That is 1 lambda. So in this information, the delta Y is the amplitude, the delta X is the lambda. Okay. Okay, and speed of the wave. In general, speed is defined as the displacement over time taken. So why are we using the delta X? Because we are talking about speed of the wave, not speed of the medium. So when we talk about the wave, the displacement must be the delta X over the time taken. Okay, so for one complete period, let's say the distance traveled is 1 lambda. Okay, so lambda over T, 1 over period, is actually the frequency. Okay, so from here we can have this kind of equation. Lambda times with the frequency is equivalent to the speed of the wave, right? If you're considering magnitude. If you're considering the direction, then we may put it as velocity of the wave. Okay, this general equation can be applied to many types of wave. Not only to the mechanical wave, it is also applicable for the electromagnetic wave or EM wave. So, take a look on example 13.8. A wave travelling in the positive x direction is pictured as in figure. Find the amplitude, wavelength, speed, and period of the wave if it has a frequency of 8 Hz. Okay, in figure, the delta x is 40 centimeter and delta y is 15. Alright, so we know that the delta y is the maximum displacement of the medium. So this is our amplitude. The delta x is the distance between crest to crest. So this is actually the lambda, the wavelength. To have v, the speed of it, is v equivalent to f lambda or lambda f. So we have 3.2 meter per second. To have period is 1 over frequency, and frequency given to us as 8 Hz. Okay, so for figure B, this is actually your homework exercise 13.8. Okay, let's move to example 13.9. A wave has a wavelength of 3 meter. Calculate the frequency and the wave if it is A, sound wave, B, light wave. So since we know that V equivalent to lambda F can be used in mechanical wave or EM wave, actually we can solve it with this equation. Okay, very simple, straight to the point. So V equivalent to lambda F, to have F, V over lambda, so you will have 114 Hertz for the sound, and then you will have for part B, you want to figure out the frequency. While you're using C, because we're talking about EM wave, light, right? Okay, so the speed of light is 3 times 10 to the power of 8, right? You may refer this to your calculator. Okay, the symbol is C or C naught. Okay, then exercise 13.9 should be your homework. Okay, proceed to speed of a wave on a string specifically. Okay, on a string. The speed of a wave on the wave stretch under some tension F, okay, is given as V equivalent to square root F over mu, where the mu is total mass of the string over the total length of the string, the mu known as linear mass density, or also simply called as linear density or linear mass density. Okay, the speed depends only upon the properties of the medium through which the disturbance traveled. Okay, so it depending on the type of the string that we use or rope that we use. Different size, different material. Is the string, the rope made of plastic, made of the fiber, made of any kind of, so different type of material will give you different value of mu, the length as well, the mass as well, the type of material as well. So the speed of the wave travel through that particular medium, that particular type of rope, will be square root of F. F is the tension of the string or rope, okay, experience, over the linear mass density of the string or rope. Okay, and to calculate linear mass density, the mu of the rope is total mass. This is actually, okay, total mass of the string, or rope over, okay, total length. Okay, sometimes given to us the total length 1.5 meter, but then not the whole length is used or being stretched and the path going to travel through. Sometimes maybe only 1 meter is used up, okay, so that the path going to travel within 1 meter only. But to calculate mu, you have to use the total mass of the string, the total length of the string. Okay, take a look on this example. Okay, a uniform string has a mass of this and length of this, and then maintained in the string by suspending block of mass of 2 kg from the end of the SE. Okay, find the speed of the transverse pulse on the string. Okay, so you see here, the one that being stretched is 5 meters. Okay, this part is connected to the block here. Okay, the weight of the block going to cause the string or rope to be stretched. Okay, so the path going to travel within these 5 meters only, not within this one. This one just to connect. Okay, but whenever you want to calculate the mu, you have to include the total length, right? So you need to add up 5 with the 1 meter there, okay, in order to calculate the mu. Alright, so the question asking for find the speed of the transverse wave pulse in this string. So, okay, we know that this is hanging here balance, so sum of Fy equivalent to 0. The tension upward is equivalent to the weight. Okay, so this is basically the same to the tension equivalent to the weight, right? And then part next we're going to use the equation of V equivalent to square root F over mu. Our F is the T, is the mg. The mu is total mass over total length of the string. So you see here, it's total mass over total length. You must plus 5 with the 1 meter. That is the meaning of total length. Okay, so you will have your V 62.6 meter per second. Okay, now part B, find the time it takes the pulse to travel from the wall to the pulley. So the effective length is actually 5 meters, not 6, okay? Because to the pulley only. Alright, so exercise 13.10, do it as your homework. We shall discuss this during our face-to-face session. Now let's proceed to the interference of wave. Okay, two traveling waves can meet and pass through each other without being destroyed or even being altered. Okay, how they're going to communicate? The wave obey the superposition principle. What is superposition principle? It says that when two or more traveling waves encounter each other while moving through a medium, the same medium, the resulting wave is found by adding together the displacement of the individual wave point by point. Okay, so in terms of meaning of it, okay, let's take a look on this diagram. The first set of diagram here is for constructive interference. Okay, and for second set of the diagram here is destructive interference. So since, okay, the first wave and the second wave having the same amplitude, positive amplitude, negative amplitude at the same instant, the same area within the same medium, when we want to total up, okay, the resultant of the two wave, okay, in terms of amplitude, we will see it is double. Okay, so this amount will add up to this amount, goes the same in negative direction. So the resultant will be the combining the two wave in part A resultant in terms of algebraically done. Okay, simple mathematics. Okay, and then for destructive, at this instant, wave 1 is having positive amplitude, but then wave 2 is having negative amplitude. This is crest, this one experiencing through. So when they meet up, add up together, we're going to have flat area. What does that mean? It means they are cancelling out each other. So that is why it is known as destructive interference. So this is one of the example for the constructive interference in a string. So we have, let's say the first situation, we have a small pulse, okay, traveling, meeting the bigger pulse, okay, in terms of amplitude. They're going to meet like this, communicate, and then going to be add up together. They're going to separate themselves and proceed with their own direction, maintaining their amplitude, their own amplitude, right? If they are having one positive amplitude and the other one is negative amplitude, what will happen when they meet up? Okay, you see the resultant slightly less than this, isn't it? Because when we add up this one, we have to put the negative sign saying that this is negative amplitude. So they're going to separate and then proceed with their own direction, maintaining their original amplitude or crest or true value. Okay, so now we're going to look on the reflection of the wave. Okay, we have two kind of reflection of the wave, whether the wave going to meet the fixed end or loose end. For the fixed end, let's imagine we have wall here. Therefore, this point is tight, very tight, okay, to the fixed end, we call it. Okay, so what will happen? The incident pulse, okay, going to meet the wall, the fixed end, and then being reflected in opposite direction to its initial direction. So if let's say the incident pulse having crest, but then the reflected pulse will be having through because of the fixed end here. Okay, the amount of it the same, but then in opposite direction. Okay, for the free end like this, let's say we have a ring here. Okay, so the stretch string is tied to a loose ring. So what will happen when the incident path going to meet the free end? They are going to travel around this, okay, and then when it is reflected, they're going to maintain the same positive amplitude or crest here, okay, due to the transfer around the ring, around the free end, we call it. Okay, this is the nature of the reflected wave when we have free end. Okay, the path is not inverted, maintaining the same situation to its initial. That's it for the lecture. Thank you very much. Okay, please finish up all the exercises and tutorial questions. We shall discuss all these examples, exercises, and tutorials during our face-to-face session. Thank you very much. Assalamualaikum.